Okay, hello everyone. We have Dr. Adam Schroeder today in our seminar, and Dr. Schroeder received his bachelor's in mechanical engineering from Ohio Northern University in 2008, and worked for 7 years designing and leading projects for automation and machining lines. He received his master's and PhD from University of Toledo in 2018, and is currently an assistant lecturer in MIME department. He directs the Robotics, Automation and Design Lab and is the program director for the graduate certificate in mechatronics. Thank you so much, Dr. Schroeder, to be here, and please go ahead whenever you're ready.
Thank you. Thank you for your introduction, Kareem, and thank you for an invitation to talk a little bit about some of the current robot experiments and equipment and techniques that we use in our lab. I'm looking forward to it. I wish we were doing this in person, but this is the next best thing. So I'm excited to share this with you. So mostly what I'm going to talk about are some of the most recent physical robot experiments that we're performing in the lab. So there are two master students of mine who graduated in the summer, and I'm going to highlight some of their work. And then related to swarm robotics, and then I'll transition to something that's still robotics, but completely different, talking about folding robots. And you could interpret folding robot as a robot that folds something, like a shirt, but I mean a robot that folds and moves its joints as a form of locomotion. So I'll talk more about that in the second half. And this is my single slide introduction to what is meant by swarm robotics, because the term's used pretty loosely, especially when it's used in media. And typically what we really mean by a swarm, or within the field of swarm robotics, is that there's many simple robots, and you can argue about how many robots there have to be for it to be many. And each robot's following a simple rule, and there's no central leader that's telling each robot what to do. So those are the main things that make it a swarm. And it's different than other multi-robot systems. So that's what it is. It's a type of multiple robot system, but it's different because it has this distributed architecture. So I hope you can see my pointer. So a robot swarm has this distributed architecture where robots are communicating only with their nearest neighbor, and they're making decisions about what to do on their own, and maybe using some of the information they gained from their nearest neighbors only, compared to this traditional multi-robot system where you have some central controller. The central controller is making decisions. It's sending information to the other robots and receiving information back from the other robots. So that's the traditional way to do it. The main advantages to using a swarm is that it should be scalable, meaning I show 5 robots over here, but I should be able to add 5 more robots, and the group works similar to how it worked before. So I don't run into some limitation on the number of robots that a central controller would be able to supervise effectively. So that's one benefit. The other benefit is that you're robust to the loss of any individual robot. So if this little robot down here has some type of failure, it stops working, but the rest of the group can continue to work just with one less robot. For the traditional approach, this is the main failure point. If this central controller fails for some reason, then the whole group fails. So it's fragile in that sense. So that's why swarm robotics is interesting. The next thing I'm going to talk about is just a very brief history of some of the major steps with robot swarms and some of the applications of robot swarms, or where it is today. So people have been working with robots for a really long time. This is one of the first important papers in the field of swarm robotics, or rather a set of papers from a particular group, a group that designed this robot platform called a swarm bot. There's nothing particularly special about it. It's just a robot platform, and there's a little gripper on the end that it can go and it can hook onto its neighbor, and then the next robot can hook onto its neighbor. So nothing special about the robot platform itself, but they started using it in new ways. So one way would be for some form of collaborative navigation. And I can give an example of trying to bridge a gap. So here there's two big boulders, and any individual robot trying that on its own wouldn't be able to get across. But by connecting them together in this chain, and then the entire chain advancing forward, you're able to get that first robot across, and then it's able to continue to move and pull some of the middle robots across, and then finally the last robot. So that's a powerful idea that an individual couldn't do something, but when I'm somehow working together with other robots, it enables some new behavior or some new capability. So that's one thing that they did. Another thing was traversing an obstacle as a chain. So here they're able to climb up over this curb, and an individual robot by itself wouldn't have been able to climb up. So again, you get new capabilities because they're collaborating somehow. Another example, which is maybe a little bit scarier, but also has an interesting name. So some form of collaborative polling, where I can form a chain like I did over here, and all the robots in the chain can move in the same direction with one of the robots holding on to something that you're trying to pull, and together you can move something heavier than a single robot could. And I recommend finding the video for this child pulling while the child just lays on this floor, and these robots drag it slowly across the floor. So an actual application for this would be some kind of search and rescue, where there's people that are injured or unconscious, and maybe you can drag them to a safe location. So this group of people developed this swarm bot and kind of popularized the idea of a robot swarm. And I'm including the number of citations with some of these papers, so you get an idea that these are really influential papers and inspired lots and lots of other research. So it's good for really understanding the development of swarm robotics. So that was 2004. And then in 2012, a group at Harvard, they created something called the kilobot. So kilo, like the SI prefix for 1,000. And they made 1,000 of these robots. So here's a 100 by 100 grid, or no, it wouldn't be 100 by 100, maybe 30 some by 30 some grid of 1,000 robots. And each robot is very, very simple. So this robot, and I guess you can see the scale relative to a penny here, it sits on these 3 legs. It has a coin cell battery on top, and then it has these 2 vibration motors on the side. And kids make vibration powered robots these days. Some of them are called bristle bots, but they created this robot using these really inexpensive vibration motors. So if they spin both motors in the same direction, this thing vibrates forward, or in the opposite direction, it goes backwards, or in opposite directions, then it can do zero turn, or zero radius turn. So it's actually not very capable in itself. You can get a pull force of a couple grams with one of these kilobots, so you're not doing anything impressive as far as pulling. And they also move really slowly, so you're talking millimeters per second usually. And their form of communication is also very simple. So underneath this round printed circuit board is an infrared LED. So they can turn that infrared LED on and it reflects off the floor, whatever surface they're moving on, and it reflects to another kilobot. And the kilobot has an infrared LED and an infrared receiver. And so it can tell from the strength of the signal how far away another kilobot is. And then you can also turn this on or off quickly and transmit some message that way. So really simple communication. And here is one of the applications that they perform with this robot. Again, these videos are really nice to view, and they're able to form an assembly, or they're able to assemble into one of these patterns. So this left one is supposed to be something like a starfish, and it's close to being done, but all of these robots on the bottom still have to make their way around, finish this leg and this leg. This one I think is just a K shape, and this one is like an open wrench shape. So it's impressive that they're able to do this, and each robot is deciding on its own what it needs to do to assemble that entire shape. So that in itself is impressive. Maybe a little less impressive, it takes a long time. So this took almost 12 hours to make. The simplest one took almost 6 hours, and they're not moving very quickly. So if you ever do see the videos, you can take a look and see how they sped it up 60 times or something like that. So this is really interesting. I don't know if you can look at this and say, I know the exact practical application that I'm going to use this for. It's great that they can demonstrate that. But that's one possibility. And moving on, so this is a robot that I use in our lab for our swarm robotics research. And this is a third generation of a robot called a TurtleBot. It's been around since 2017, and it's definitely more capable than something like a kilobot. It's got normal differential drive. So I have a motor that drives this wheel. I have a motor that drives the other wheel. I can move forward. I can spin in place. It has a Raspberry Pi single board computer for running the programs for controlling it, and also Wi-Fi capability, which is how we can communicate with it and how they can communicate with one another. And the last thing is this LiDAR sensor on top. So it sends out a beam of infrared light. It hits an object, reflects back, and we can time how long that takes and measure the distance that some object is away from the robot. And then I can rotate this top head of the LiDAR unit continuously and get a picture 360 degrees of what's around the robot. It's only two-dimensional, so you're basically sending out a light here and then rotating in here and here. So you get a plane of information. There are three-dimensional LiDARs out there too. And so using that, you can build maps and you can use it to autonomously navigate. One of the popular fields of robotics research is called SLAM. It was popular maybe 15 or 10 years ago, and now it's a pretty mature technology. So SLAM stands for simultaneous localization and mapping. So I'm able to build a map of the environment around me, and also able to localize myself or tell where I am relative to parts of that map. And then once I do that, I can use it for autonomous navigation. And this other reason this robots is pretty interesting, it's the most popular open source robot platform for using something called the robot operating system. The robot operating system, it's framework for easily getting robots moving and integrating new sensors and integrating new behavior. So it's really widely used, especially across universities for robotics research, and also for some commercial platforms, commercial robot platforms. So it's a great platform. No one has really used this for swarm robotics research that we're really aware of until our lab group started using it. And we have about 50 of these turtle bots to use, so we can do some interesting things with them just because of the number of robots. So I'm going to transition to talking about some of the recent experiments in the lab now that I've given some context. And this is the work from Sheershak Adhikari. So he graduated in the summer, and he's working for Amazon now as a robotics project engineer. So the first thing that he worked on is something called a conveyor bucket brigade, which is a new type of behavior that we had an idea about and then we implemented. But there is a behavior called bucket brigading that people have used with robots for a while. So bucket brigading, it's the idea like an old fire department. You form a line of people from a water source to the fire, and you pass buckets from the previous person to the next person, and you can very efficiently and quickly pass a lot of water that way. So you could do that with a robot too if you had some kind of arm manipulator to grab a bucket. But we decided that we wanted to make a conveyor bucket brigade where each robot has a conveyor mounted to the top, and that's how I can pass an object from one robot to another robot. And putting a conveyor on top of a robot, it's not novel. Plenty of people have done it and are doing it, and some robots used for logistics within warehouses work just this way. They have a powered conveyor on top. So that's not what is unique about it. What is unique about it is when we add more robots, say, for example, we go from 2 robots to 4 robots, we can actually pass more than twice the amount of materials when we double the number of robots. So it's not a linear improvement, it's actually a super linear improvement. Double the robots, you more than double the amount of materials that they can transport. So that's why it's really interesting. And I'll show a plot on the next page. But first, let me show this video. You'll see Sheershak loading these robots, and you'll also see they don't work perfectly every time, but I'll let the video play. So these little pieces of wood are what we're using to transfer from one location to another location. Once it's loaded, it advances it on the conveyor, and then the conveyor robot moves to the next conveyor robot. They pass it across, and after it's transferred it, then it moves backwards to meet the previous robot and collect another object, another piece of wood. So this is the conveyor bucket brigade, and for this exact experiment, you could perhaps only fit one more robot, and then this space from the pickup position to the drop-off position would be completely occupied and the robots wouldn't be able to move. So this is the maximum number of robots we tested. And here's a plot of some of the data. So we tested up to 4 robots where a single robot could transfer, I think, 2 objects in the amount of time we allowed for the experiment, I think maybe 5 minutes. But when we increased it to 2 or 3 or 4 robots, we we exceeded a linear performance improvement. So if a single robot can do 2 in that amount of time, a linear improvement says that 4 of them could do 8 in that amount of time, but we're actually able to do more than that. And the red box is what we were able to accomplish. A blue triangle up here shows what should be possible if you get a perfect pass from one robot to another robot every time. And so that's something that we're still working on to be able to get a perfect pass every time or most of the time. But we're still able to demonstrate that this super linear performance increase is there. And the reason that it's there for this example is that the robot can advance something it's carrying from the pickup position to the drop-off position in 2 different ways. First, just by the robot moving in that direction, and second, by advancing the part on the conveyor at the same time that the robot's moving. And if there's just a single robot, you can only take advantage of that one time. So if you imagine there's just a single robot moving to the right, it can advance its part on the conveyor and move it to the end while the robot's moving, but that's it. If I add another robot, I can take advantage of that 2 times. So the second robot can also transfer it or advance the conveyor while the robot's moving to the right. So that's an interesting place where this super linear performance is able to be achieved. Sorry, I'm just checking the time here because I can't see it on my screen very well. So that's the first experiment that Shearshak did. The second set of experiments that he led was related to collaborative polling. And it started with a senior design team who tried to design a way to easily connect one turtlebot to another turtlebot so that they could form a chain and that they could together pull with more force than any individual robot could. So I'm showing a few pictures here. One is a picture inside of our lab. And I think we did up to 30 robots in a line indoors, so a single chain. And we could measure their pulling force with this digital scale as we continue to add more and more robots. And the senior design team came up with this really simple way of using a 3D printed S-hook to connect one robot to another robot. And after they developed this, then Shearshak was able to go through and repeat a lot of their experiments and collect some data on how the pulling force scales with the number of robots. And I'm showing his data here. We're not convinced yet that it's super linear, but we're continuing to investigate this. There's a new master's student who's trying to replicate some of these results and get a better understanding of, as we add more and more robots, what happens to the pulling force. One reason we're interested in this, that first slide I showed from 2004 with the swarm bots, they showed that when you added when you started with 3 robots and added a 4th, you more than linearly could increase the pulling force, and there were some specific reasons for their experiment. So that's one reason we're interested in this. And the senior design team was able to accomplish what we set out for them, which was to pull my pickup truck in neutral, which took 70 some pounds of force, and they were able to actually move it. So that was their grand goal that they were able to achieve, but really were interested in creating or gathering data to create a plot like this. Okay, I'm going to move on to another student's work. So this is Corey Williams, who graduated also in the summer. And he picked up on some work that I had started a while ago, which involves taking an area that multiple robots are working in and breaking it up into individual regions, and then each robot would only work within its own region or within its own partition. And what Corey was able to do is write code so that robots talking only to their nearest neighbors would be able to come up with partitions where each robot had about the same amount of work to do within its partition. So one thing that Corey compared was if we simulate this on a single machine, that each robot is trying to find a good way to partition, it can happen really well, or it can happen without too much delay. So what this plot is supposed to be showing here is each gray line would be one of the robots and the amount of work in its current partition. So some start off with lots of work, some start off with little work, and by moving the partitions around, they can try to reach some equal amount of work in each partition. So this is showing that over time, they're able to converge until each robot has about the same amount of work. And this red line is supposed to show the error or the difference between the maximum amount of work that one robot has to do and the minimum amount of work that robot has to do. So you're trying to minimize the error and try to arrive at the same amount of work. So when you do that all on a single computer, there's no kind of delay due to communication. But when you do it on separate robots, and they all have to have to communicate back and forth over some kind of wireless network, there's a lot of delays and other things that can go wrong, like missing a message along the way or not performing my calculations as fast as the robot next to me. And so convergence for that case looks a lot messier. So same thing, some robots start with more work, some robots start with little work, and they move partitions around and get to something similar to all the other robots, but the error is a little bit higher in this case. So Corey was able to compare those two cases, which is interesting. And then he was able to demonstrate his partitioning algorithm for a particular application where we decided this is the area that we wanted to work within. And we were going to put hardware, little nuts and bolts, other things with iron content on the floor. And each robot would have a bar magnet mounted to it. And after the partitions were made, so example partitions might look like this in the bottom left, then each robot would move through its own partition, parsing back and forth, working to pick up all of these nuts and bolts. And if this algorithm worked well, each robot would have about the same amount of hardware that they had picked up. So this isn't hardware that's just spread out everywhere. It's hardware that is highly concentrated in some areas, which is supposed to be a bright pixel here, or has a lower concentration in other areas, so a medium darkness pixel, or none at all, so that would be a black pixel here. So it's not homogeneously distributed everywhere. Here's an example of that bar magnet mounted to the robot, and just manually picking up a bunch of this hardware so you can see how it's able to collect it. And I'm going to show this video on the right-hand side. So this video shows the entire process starting from robots at some initial position, robots trying to come up with good partitions so each one has the same amount of work, and then after the partitions are made, moving to their partition, and then moving within their partition and picking up that hardware. So it's showing this video from above, and it's also showing a screenshot from some of the software, the robot operating system that we use to visualize what's happening. So in the top left here, this is a robot's position, this little black shape, and the blue part is the center of a partition. And so initially, these are random, but you're going to see the position evolve over time as I start to play this. Okay, so they're starting up, and then we're going to see the center of these partitions start to move around. And this is really a control problem. You're trying to move them to minimize the error, or minimize the maximum amount of work in any partition to the minimum amount of work in another partition. And after a while, they stop moving as quickly, so it's settling to something near equal work in each partition. He ran it for longer than we really need to have reasonable partitions, so I'm going to fast forward. And then once each partition's established, I paused it here. Each robot comes up with a set of waypoints inside of its partition. So this partition in the bottom right, it's going to move from this red waypoint to one across this partition, and then to the right, and then down, and then to the right, and then up, and then to the right, and then down. So that's how it's able to parse back and forth. So now that these partitions are formed, robots are moving, I think, to the center of their partition before they start moving around their partition. And you can see this one moving back and forth right here. So it's not exactly on its waypoint, or it's not within the tolerance that we set. So it's moving back and forth until it's happy with its location and its orientation. So right now, almost every robot's moved to the first waypoint in its partition. And now Corey goes in and he adds the bar magnets to each one. We didn't want to add them earlier because we didn't want to pick up these materials just on the way to the starting positions. So each robot now has this bar magnet installed. And if we follow any particular robot, this one's moving to this red waypoint, it's turning, and then I'm going to start moving down to this waypoint on the bottom, right here. And I'm sorry if you weren't able to see my cursor there. So I just turned on the laser pointer. Then it's going to move to the right. And when it's happy that it's reached that waypoint, then it's going to move to the next waypoint up here. Okay, so I'm going to skip ahead, and you can see these little black dots on the floor. This version of the experiment, we just spread the black little hardware everywhere so that we would be able to visualize, did we actually move through the entire space exhaustively? So this one's moving down, and you can see as it moves in its path that's already covered, there's no hardware behind it. So I'll fast forward to almost near the end, and there's still a few pieces of hardware, that they didn't pick up, and that happens for different reasons. One is allowing some space from one partition to another partition so that robots don't collide with one another. But it shows and demonstrates the idea. So this would be some kind of cleanup application where you want to exhaustively move over every part of a work area. Okay. The next slide here, it's my last one talking about swarm robotics. So one thing that you can think about is, can you even create a robot swarm that's fully distributed? So there's no centralized aspects to it at all. And it's actually pretty difficult to do that. So the system that I've been showing these videos of in the lab, it's really more like this centralized system because we have a controller, or we have a laptop here that we're able to view data from each robot. And we have a single router, and each robot can talk to its neighbors, but it does it by passing messages through a router. So that's, in that way, it's still centralized, even if it's only talking to its neighbor and not a single controller telling it all of the information. So it's always going to be difficult to completely decentralize a system or have a completely distributed system. And so one reason is if you have some kind of communication like Wi-Fi that's centralized, there are ways to do that decentrally. Or if you have some kind of human that wants to follow the progress of this group of robots, somehow you want to be able to observe information and sensor data and the state of each single robot. So in the process of gathering that information, you're creating some centralized connection. So maybe the gold standard isn't creating something that's fully distributed, and there might need to be some centralized aspects that are still present for this to be useful. All right, I know I have maybe 10 more minutes, so I'm going to transition to talking about another area of robotics research that we do in our lab related to folding robots. And people have been building these kind of robots for a while. The reason that these types of robots are intriguing is, one, that we could put them in a flat configuration or fold them into a flat configuration. And if we do that, we could more easily transport them from one place to another place. So whether that's somewhere in space or somewhere domestically on Earth, you can just transport it more easily if everything is flat and compact. Another reason that these are interesting is many of the manufacturing processes that we use work well with two-dimensional planar materials. So processes like lithography or laser machining or pick and place component assembly for circuit boards. So we've got a lot of manufacturing processes. It might be a new application for them if we can use them to make these types of folding robots. So this was a pretty influential line of research done by a group at MIT, and they designed software and these robots that could go from a flat state and using motors go to a deployed state and then use motors for mobility so that it can move around. So they're a group that contributed a lot in this area. I'm going to show now some of the work that we've been doing. So starting in spring 2021, there's a senior design team that my lab worked with. Josh Stanley was an undergrad student that worked on that team, and they designed and constructed this toroid robot, or this donut-shaped robot. And we were interested in this shape to begin with because you could get lots and lots of different configurations and different possible gaits or forms of locomotion with this many servo motors. So each of these little arms or loops has 3 servo motors. So times 6 is 18. And this internal hub has another 3 servo motors. So I think there's 21 total. And so with that, you can do things like achieve rolling gaits, like this one. You can have different forms of walking gaits. So the group called this the gorilla gait. So it's picking up these legs and then dragging the rest of the robot forward. There's a crab gait where it's sidestepping, so moving side to side. And the team tried this out on different types of terrain and was able to get all these different types of gaits to work, including transitioning from flat, like the still image here, to vertical, like this rolling. So being able to go back and forth between them. So that's one type of folding robot that we've explored in our lab. The second slide I'm going to show is a simpler version of that previous robot. So this slide, you can see each one of these legs, it's actually made up of 6 panels. So 1 at the base, 2, 3, 4, 5, 6. So this robot is like one of those individual loops. And so you can call it a hexagon robot because it has these 6 sides. There are 3 servo motors inside, and that's how many degrees of freedom this shape has. So if we use 3 servo motors, we completely control all of the other angles in this structure. And so we can achieve some different forms of locomotion with this simple robot too. So this is rolling. You can get something that resembles how a tank tread moves. And we're able to collect data on exactly where each point or each hinge in this robot has moved with time using a camera motion tracking system. And these pictures don't have the little markers attached to the robot, but we can attach a marker at each one of these joints and then use our system to track its exact position over time. So that's a 6-sided version, a 6-sided robot. We've also been working with a cube, which is, if you think of this 6-sided robot, it's like a 4-sided robot where you only need a single servo to define, or the square only has a single degree of freedom. So you only need a single servo to define all the angles. But where it's different and interesting is this robot, if I wanted to, I could move the servos so that the center of mass was ahead of whatever panel was in contact with the floor. And if I do that, it makes the robot roll. So I can achieve that statically. With this cube, I actually can't move to get the center of mass over outside of the panel that's on the floor. So I can't make it roll that way, but I can take advantage of this dynamic effect and use the angular momentum to allow it to roll. So here's our cube rolling. And we've been developing that over time. So this bottom right picture, it's showing a sequence of some of the prototypes that we built, and we're 3D printing all of these, so we're able to prototype them really quickly. And we've done more than what I've showed in these videos, so I'll have a few pictures I'll mention here, but some of our interests are characterizing these different rolling gaits, like their linear velocity, how efficient they are, so how much current and energy does it take to move one body length of the robot, and understanding the underlying dynamics, and also how we can use some different gaits depending on the terrain and maybe a uphill grade or a downhill grade that we're trying to traverse. Also designing some control systems that can use an IMU to tell the orientation of the robot at any point in time. And then we've also been interested in integrating these shapes in new ways, like using them as a wheel for a robot. So this is an axle in the middle with one of those hexagon robots on each end and some springs to connect a hub to that hexagon shape. And so we're able to then drive it forward with both of them rolling forward or backwards or make it turn in place. And we've come to find that NASA JPL has done and built some similar robots. So this one's called the Axle. And this one in the bottom right, it's called the Puffer. So it's able to collapse its wheels. And that's one thing that ours is able to do too, except we're collapsing our wheels straight down to make them flat and stow it. So Dr. Treese was able to point out these examples to us. And then also we've been looking at different geometries, like if we have a round here instead of a flat panel, can we move more efficiently or can we move faster? And so you're approximating a wheel, and we're trying to fully understand the dynamics of this system that's pretty simple, but also complex. So I think I finished with about the right amount of time. So I want to point out that this is the work of Shearshock and Corey. So they were the ones working with the TurtleBots, and Josh Stanley has been working with the folding robots and prototyping new ones every day, including some that I just saw this morning. And here's part of our research group over a winter break doing a TurtleBot test day in the Brady Center. So that's all that I have to present, and I'd be happy to take time to answer questions.
Thank you, Dr. Schroeder, for this nice presentation. I think we have a question here. In a slide from Bilal, in slide 12, how are the bots able to map the boundary of the area?
Yeah.
Okay, you can see the question. Okay.
Good question. So this area that they're working within, we use the LiDAR on the top of the robots to build a map. So they can use the LiDAR to detect how far away any of the walls are and use this SLAM, simultaneous localization and mapping approach, to build a map. So we build a map using one of these robots. And we did that before the experiment. And so the map boundaries were known ahead of time.
Okay, other question from Jamal. Okay, I'll just read the question. Swarm robots have been mostly implemented in laboratory and controlled environment. My question is, in your opinion, how far are we from seeing real world application of these robots?
So I think that's a good observation. People are doing things like working with these kilobots, and they can make patterns, but so it's hard to see, I think, some practical applications for something like this, but there are a lot of technologies that are already being used that are related to swarm robotics. So wireless sensor networks. That's very similar to this robot swarm, except each component or each device within the networks maybe not mobile, not moving. So we do see some of the same technologies used for wireless sensor networks. One reason I think they're not adopted for industrial applications, or that's a stumbling block, is kind of the magic behind swarm robotics is what simple rules do I tell a robot, an individual robot, to follow to get the group behavior that I want? And it's kind of unpredictable. And in industry and manufacturing, we want things to happen the same way every time with predictability. So I think it needs the right application for them to be applied to real world problems. And that's something that I'm really interested in. So I think something like this, it's very applicable to a real world problem. This is something that would be happening inside of a warehouse, and some type of collaborative polling. Anytime we need to pull something, and you can think of lots of examples when we need to pull something. Agricultural equipment, it's all about pulling different implements. So why isn't it ubiquitous? I'd say some of those reasons, like we don't they don't act the same way every time necessarily, and they maybe just haven't found the right application yet. But some of the individual technologies are certainly being used.
We have a following question from Bilal. For the folding bots, are they all using the same microcontroller?
Yes, so they're all using an Arduino, and the Arduino uses this microcontroller from ATmega. So every one of those folding robots, that's what it's using.
Okay, I have a question about this slide, cooperative polling.
Sure.
You do any modification for those turtle robots, or are you just studying the polling force versus the number of robots?
Yeah, so these right here are shown basically unmodified as you assemble them, whatever their capabilities are. Each one's about 2.2 pounds, something like that. The senior design team, their goal was to pull something with a specific amount of force needed, this truck. So we're able to measure that with a scale like this. Yeah, I don't know if you're able to see my cursor, but
Yeah.
you can generate so much more pulling force by increasing the mass of these robots. So when you increase the mass, you increase the normal force. And because you increase the normal force, you're able to increase the friction force or traction force on the tires. So just doing that, mechanically changing them, is an easy way to get more pulling force. But we were more interested in what happens when they're collaboratively pulling, or what are some algorithms that we can use to increase the pulling force when they're working together. So more on the control side or the algorithmic side.
Yeah, thank you.
And I saw a follow-up question from Bilal here.
Yeah.
Great question. So let me see if I can make this large. A short answer is that it barely fits, and that if you want to hold it in your hand, you're welcome to come visit our lab. But you can see there's a proto board here with a small version of an Arduino soldered to it with also this RF module so that we can control it remotely, and and then also mounting points for the servo connections. So we couldn't make our cube much smaller, especially because when you start to change the angle, then you might be interfering with something that's on the inside. Thank you, Dr. Kaur. One nice thing about this TurtleBot is it comes with a lot of basic code that you can use directly, like you can just use the SLAM code that's written, and you can do some forms of autonomous navigation, including being able to navigate around obstacles, but it's just building whatever, it's just using whatever its built-in algorithms for that navigation are. So I'm sure that you could find situations where it didn't perform well. And I can see some of the comments. Kareem, is it okay if I reply to those?
Yeah, there is. Okay.
Thank you, Debbie. And Andrew said, do you think using a combination of collaborative polling and partitioning would allow robots to perform tasks like disaster recovery at some point in the future? Yeah, so one of the ideas is that these robots have a menu of different behaviors and capabilities, and that you can poll when you need to poll, and you can pick up when you need to pick up, and you can connect together when that's advantageous. I think the biggest hurdles could be if something like disaster recovery or hazardous cleanup. Every example you can think of has some specific things about it that make it challenging and might be hard to design a system that works well overall. You know, if there's rubble on the ground, are you able to communicate or not? So it's kind of hard to make a general purpose system that autonomously would be able to move back and forth between behaviors when it needs to switch from polling to cleanup, for example. So there always needs to be a human in the loop somehow that's giving some feedback to make it work for specific situations. Bilal asked, for the polling robots, are they all polling simultaneously? Yes, and their wheels are all slipping. So it's continuous slip. So I'm sure that there's improvements that can be made by using some kind of traction control or some kind of ramp starting. Thank you, Dr. Elhinian. Thank you, Amir.
Okay, any other questions? Okay, if not, thank you so much, Dr. Schroeder, for this nice, amazing presentation. Thank you all for attending and for the questions, and we'll see you in the next seminar. Thank you.
Thank you for the kind words, Kareem. Nice to see you.
Nice seeing you. Bye-bye.